I'm going to tell you very quickly what are the main challenges when it comes to learning mathematics. Then, because this session is specific to data science, I'm going to draw examples from the mathematics and data science. What I'll be talking about today is not specific to math just for data science, but mathematics in general. But the examples I use will be from data science. Then I'll talk about the relevant mathematical branches. Math is a huge domain, and data science, well, so is data science actually, but some mathematical branches are more important than others. So there's a slide where I'll tell you the hierarchy of the mathematical branches and their prerequisites, and then how you want to go about gradually and progressively accumulating, let's say, mathematical literacy, for lack of better words. And specific to learning math, because in data science, there are two technical pillars, let's say. The first pillar is statistics, and the second pillar is computer science. The third is, and I'm assuming you know this, domain knowledge. But the two mathematically technical pillars are statistics and computer science. Now, the statistics that we are talking about depends a great deal on mathematics. So to keep things simple going forward, I will interchangeably call the statistics pillar the mathematics pillar. The way you would go about learning the mathematics pillar is quite different. And that's why I have a learning template. And of course, we'll finish it off with some excellent resources for you to get started with. The challenges with learning mathematics, there are two main things. And you want to be acutely aware of this whenever you come across a video, you attend a workshop like this, you pick up a book, you come across a blog. There are two things that you need to be aware of. Number one is terms. Terminology used in mathematical literature. You might now and then see a word, and you have to make sure not to mistake this with a word in English. For example, the word sample, or the word space, or a word like derivative. Now, these are words that are available in the English vocabulary. They can be used in everyday words, but in mathematics, they mean something very different and something specific. And the second one, perhaps what many find intimidating and something that obfuscates the idea that is being expressed, is the notation. The different uses of the English letters, why sometimes we use letters from the start of the alphabet, other times from the end of the alphabet, other times we pick letters from the middle of the alphabet. And then we use Greek letters, sometimes Hebrew letters. And then there are these special looking symbols that are completely made up and unique to mathematics. So keep these two things in mind, because when we come to the learning template, I'll tell you how to, let's say, tackle these two obstacles or manage these two challenges. Whenever you see a mathematical expression, do not attempt to understand what it's saying just by looking at it. You see, studies show that the human mind, can only keep four things in its train of thought. So if you're trying to, let's say you have a grocery list, right? You want to go to the grocery, you want to buy some stuff. You can remember four things at a time. Now, of course, there are some tricks you can use, like mnemonics, or use some sort of storytelling pattern to remember more items. But you can only keep four things actively in your conscious. Now, when you're looking at a mathematical expression, almost always you're going to be looking at a mathematical expression that has more than four terms, like letters, symbols, what have you. So even if you do have a mathematical background, if you still attempt to look at it and try to understand what it's saying, you're not going to be successful. Mathematical expressions are analogous to sentences. Now, depending on what that mathematical expression is, it could be as small as a phrase or it could be as big as an entire page of paragraphs. So if you try to look at the mathematical expression and try to make sense of it without actually writing it down, it will be like trying to read an entire paragraph just with one look, as opposed to reading it, word by word. And so if you try to add a fifth, let's say you're trying to read that expression. Now, what expression that is doesn't matter. Just conjure up one in your mind. Now, you can keep track of the 4 terms in the mathematical expression, but if you try to add the 5th one, your whole train of thought falls apart. So, what's the approach? Now, let me say this before I continue any further. Videos are convenient. They are quite accessible, and you have a lot of excellent video material online. For example, the MIT lectures on YouTube, the Stanford lectures on YouTube, they're free, they are mathematically rigorous, they're taught by experts. But it is actually better to learn from text than videos. Now, I'll talk about why that is once we get to the learning template. But let me quickly summarize what I'm going to say and what my ideas are for the remainder of this workshop. Whenever you come across mathematical expression, even if there are only a few terms involved, write them down. If you see an equal sign, write it down. If you see a function notation, write it down. Whatever you see and you try to make sense of it, first write it down. And then you want to make sure you have quality material. What do I mean by quality material? I mean material that is written by an expert on the matter, and not some random YouTuber, or for that matter, someone who's on who's on Meetup and hosting a workshop. So I don't know how many of you looked me up, but whenever you do want to learn something technical, make sure that person definitely knows what they're talking about. So, for example, you would pick up a textbook, like a university textbook, because a person who authors a textbook cannot publish that textbook unless the work has been reviewed by their peers who are also experts on the matter, and the book has gone through several revisions to make sure that typos, any sort of mistake is accounted for. And then they have things like errata. So even if someone finds an error, they will publish that, and for the next edition, it will be taken care of. And then yes, if you want to become a data scientist, you're gonna have to become a mathematician. Okay, let me say that again. If you want to become a data scientist, you have to try to be a statistician, and to be a statistician is to be a good mathematician. So a good data scientist is a good mathematician. Okay, now not everything you will do will involve mathematics. Computer programming is another aspect, but the majority of your work will involve mathematics. So if you want to become a competent data scientist, and that means that that means you're saying that you want to become a competent mathematician, you have to learn to study from text, not videos. Videos have their place, but your first starting point should be text. Okay, but let's continue. Let me justify my points here. So very quickly, let's talk about the organization of data science. This will be quick. So here we have data science, and it is a field that sits at the intersection of 3 other fields. The first one, the main one, and perhaps the most important one, is statistics. Okay. The second one is computer science, and the third one is domain knowledge. Now, statistics is not a branch of mathematics, but it heavily relies on mathematics, and in particular one specific branch of mathematics, and that is probability theory. More on that later. The second branch is computer science, but computer science is a big field, and a data scientist does not need to be, realistically speaking, they cannot be an expert in all the areas of computer science. So there's computer networking, there's computer architecture, operating systems. But 2 things you want to emphasize in the computer science area. And the first one is computer programming, that goes without saying. The second one is data structures. Now, companies use the job title data scientist somewhat liberally. So a data scientist in one organization could be more of a researcher, more of a mathematician, whereas in another company, they could be more of a data engineer or more of a programmer, a machine learning engineer. So these terms don't have a very definite meaning or it's not a job title that is used uniformly in all companies, in all organizations. But when I say data scientist, I'm referring to someone who uses mathematical methods for statistical inference, and to some extent they may even develop new mathematical models. So they are involved in research. So the majority of their work will involve statistics and by extension mathematics, some computer science. There is some overlap when statistics and computer science have some overlap, but strictly speaking, from computer science, it will involve computer programming and data structures. And the third is domain knowledge. You're using data science techniques to solve a specific problem in a specific domain. Banking, healthcare, real estate, biology. Yeah, a data scientist must have all three. But the first one is the most important. Now, just for extra clarity, we have machine learning and data engineering. So machine learning will fall under statistics. In fact, machine learning extends the techniques from statistics. It borrows techniques from statistics and then, develops it further. Classical statistics, for the most part, involves equations. Machine learning takes those equations and adds, additionally to it, algorithms, which is what you would find in computer science. Now, what I'm about to show you is in reality is not so well, demarcated and not this fixated. There is overlap, but this hierarchy that I'm showing you is not so inaccurate. Let's just say that. So let's start from the top. Mathematically speaking, neural networks are combinations of these mathematical structures we call matrices, mathematical operations on these matrices, which involves stuff like convolutions, scalar multiplication, and even differentiation of the values inside the matrix. If you do not know what these are, that's fine. Okay, I'm just trying to give a definition. Now, the prerequisite for neural networks, because they involve matrices and differentiation, the mathematical branch that involves a special type of a matrix, which is what we call a vector. A vector is like a row or a column. But yeah, the mathematical branch that deals with vectors and differentiation is a vector calculus. Another name for vector calculus is multivariate calculus. Or if you're a university student, it will be called calculus 3. Now, vector calculus in turn, because it involves vectors, will have a linear algebra as a prerequisite. But of course, linear algebra is not just a prerequisite for vector calculus, it is also a prerequisite for machine learning. Machine learning uses many types of mathematical techniques, equations, systems of equations, matrices, algorithms. But a subset of machine learning algorithms involve linear algebra, like support vector machines and others. Now, linear algebra in turn, I should have put it here, but there was not enough space. Linear algebra is one very important mathematical branch, and many people struggle to learn linear algebra. Understanding linear algebra very well will really empower you to understand and appreciate machine learning and neural networks, and more broadly speaking, data science. The thing is why many people struggle to learn linear algebra is because they don't know that there is a prerequisite for linear algebra. And the prerequisite for linear algebra is actually basic abstract algebra. Not all of abstract algebra, basic abstract algebra. Abstract algebra, in turn, its prerequisite would be classical algebra. The algebra you learn in school, middle school, high school. So linear algebra is actually a branch of abstract algebra. Abstract algebra involves sets and operations on those sets, the rules that apply to how you can work with one set, the things you can do to that set, the things you can do to the elements in the set. And there is one special type of set that is so important to us, especially when it comes to computers, because they are involved in computer graphics, optimization, and all the practical applications that stem from these, that a new branch was born out of abstract algebra, and that is linear algebra. Linear algebra involves these special types of sets, which we call vectors, and that's what a vector is. Now, I don't mean to throw you off with the jargon, but since this is being recorded, it could help for you to come back and watch this video to review what we're talking about here. Now, another prerequisite for machine learning and everything above machine learning is statistics. Right? Neural networks and machine learning is about applying statistical techniques on large volumes of data. Because if you think about it, statistics has been around for a while. Why not just ask everyone to become a statistician? Because while statistics tells us how to infer from data, it does not tell us how to deal with large volumes of data. And this is why machine learning came into existence, right? Machine learning took the ideas of statistics, the ideas from computer science that tell us how to work with large digital data, combine them to give us machine learning, and then the larger field of data science. Statistics, like I said, statistics is the only topic here that is not is not a branch of mathematics. It is actually a science, like psychology, chemistry, physics. You can call them applied mathematics if you want. So the reason it is here is it's just for reference, but it is not a branch of mathematics. The mathematical part of statistics is actually probability theory. If we take out probability theory from statistics, it just becomes basic arithmetic. So if you want to calculate something like a mean average, that's just addition and division. Nothing, extraordinary. But the thing that makes statistics difficult is probability theory. And why is probability theory difficult? Here I've put two prerequisites, single variable calculus and discrete math. But this is just for, let's say, basic probability theory. Let me take you to the next slide. If you were to pick up a book with the title Introduction to Probability Theory, or if you were to find a tutorial on YouTube, probability tutorial, you wouldn't get too far. Why? Because that video, let's say if it were a university lecture, or that textbook would assume you know that there are prerequisites for probability theory, and you've seen them. You know what they are. In fact, if you were to enroll yourself into a university course, or even if you were to buy a book, they would mention the author assumes, or we assume the reader knows ABC. Those ABCs are what you see here on the screen. Probability theory, right at the start, depends on combinatorics. So you may have heard of things like permutations, combinations, factorial, which we're going to talk about, by the way, in a moment. Another name, some people will say another name for the branch of combinatorics is discrete mathematics, which I had in the previous slide. But this is the basic, like the introductory parts of probability theory will definitely depend on combinatorics. And then as you progress into later chapters of that book, you will encounter what we call probability distributions. And to a probability distribution, it will tell you, the concentration of a probability. If you have data, for example, what parts of that data are more probable than others. If you want to measure probability, you will have to use definite integrals. So measuring area under the curve. I'm sure you've heard of it, even if you don't remember how it works. But what I'm saying is that you would need definite integrals. Now, definite integral is something you learn in calculus. And I've put here analysis because analysis is this umbrella, this super topic that contains calculus. So what I'm trying to say is that if you want to make sense of that page in that probability theory book or that slide in the university lecture, you have to know things like definite integrals to measure the probability, limits to know what it means for a number to converge, series to know to understand why a probability distribution function is expressed in a certain way, differentiation to understand how a probability distribution function has been derived. In fact, there are the two very important components in probability theory are random variables and their probability distributions. So these components require good background in at least single variable calculus, which requires the topics I told you about. But then because the second component is random variables, that involves sets, set builder notation, operations on sets, and that is something you would find in combinatorics or discrete mathematics, depending on how, for example, the person who has authored the book chooses to define that particular branch of mathematics. Now, I'll talk about combinatorics a little more, but if I take you to the previous slide, you'll see that I put it here at the bottom. This is the starting point, by the way. So if none of you have any experience with any mathematical background, and for that matter, you're intimidated by mathematics, this is the best place to start. I'll get into it later on, but the reason I say this is a great place to start is because discrete mathematics has no prerequisites. It is really simple. You do not need to be good at arithmetic. You do not need to know trigonometry. It's very easy. It is very easy to learn. At the same time, it will give you superpowers. It will allow you to quickly accelerate your learning of both mathematics and computer programming. Why? Because computer programming is actually discrete mathematics. But more on that later. Anyway, and then eventually you'll get to things like high dimensional probability. So dimensionality means, for example, if you imagine you have a data set with many columns, that is a high. The more columns you have in the data set, then the bigger your dimensions. And so the mathematical branch that tells us how to deal with large dimensional data is linear algebra. But I told you before that linear algebra involves basic algebra. But then there are more advanced parts of probability theory that will require not basic abstract algebra, but more advanced parts of abstract algebra. And of course, both linear and abstract extend and borrow ideas from classical algebra. And that's not all. Depending on what type of machine learning model that you're looking at, because you're in this workshop because you want to learn mathematics, not for the sake of mathematics, but mathematics for data science. Well, data science is, there are many models. Some are easy to understand. They're quite elementary. Others are quite sophisticated. And so you need to know that probability theory, in turn, probability theory is itself a prerequisite for more advanced branches of mathematics, like dynamic programming. Programming doesn't have anything to do with computer programming. Dynamic programming is the branch of mathematics used in reinforcement learning. So reinforcement learning at its core implements ideas from dynamic programming. And then there is stochastic calculus, which borrows ideas from calculus, probability theory, and this is a central branch of mathematics in finance. And then, of course, neural networks. So it's good to know this whenever you come across a topic, to know what the prerequisites are. Now, it's one thing to know and appreciate that some branches of mathematics are more advanced than others. Some have prerequisites, whereas some have fewer or no prerequisites. It's another thing to actually go about learning. And that's what the next slide is about. The next set of slides are about. A learning template. How do you do this? This is a template that I've come up with. And it's a template, and it's a system, let's say, that has allowed me to look up and understand any mathematical expression, even if I have not seen it before, and it allows me to do it very quickly, without having to go to enroll in a course or spend hours on YouTube searching for a tutorial. And if you do not have a systemic way of learning mathematics, this can potentially help you very quickly become, let's say, more mathematically proficient. There are 3 things that you need to make sure to do to fully understand what that idea is about, what regression is, and how it works, and why it's expressed a certain way. Why gradient descent is expressed a certain way, why it works, why it's used, where it's used, why it's called gradient descent even, right? These 3 things should give you a full comprehensive understanding of that mathematical idea. So not just know what the formula looks like and write it down, but actually why the formula even looks that way. The first thing you want to do is define. Find the definition. And I'll explain what that is. Then you want to know the applications of this mathematical technique or this mathematical expression. So for example, Bayes' theorem. You've seen the expression, you know what the terms are, but where is it used? How is it used? When is it used? And then third, this is the more advanced part, derivation. Formulas, like E equals mc squared. Very simple looking. No scary symbols. Normal distribution. That's actually messy looking. Gaussian distribution, that's what I'm about to show you right now, right? Linear regression. These are very, or it's the general regression model. Their formulas are very neat, compact, tidy. But that is not how they started. The person who came up with that formula did not start out with this nice, clean, compact, sleek looking formula. There was a lot of mess. There was a lot of thinking, a lot of brainstorming, and a lot of eliminating this and that before it eventually shrunk down to this nice, compact looking equation. And you want to know how that mathematician arrived at that compact looking formula. So for example, Bayes' theorem. It's very simple looking. Why is it called a theorem? Why is it a big deal if it's so simple looking? How did the mathematician get to something so simple looking? But let's start with definition. How do you handle a mathematical expression? Look at this one. The one on the left. This is the PDF of the gamma distribution. The reason I use this for 2 reasons. Number one, I intentionally picked something that is relatively difficult. I wanted to pick something that I would assume nobody would understand, so I can show you how to actually make it something you can understand. And because I was answering someone's question. The person was a computer science student and said, I know the formula, I know how to write it down, but I cannot make sense of it. I know, for example, if I plug in numbers, what I will expect, but why does it look this way? So let me tell you how we can do this. So the first thing you want to do, that's 1.1, is to enumerate. That means to count and write down everything you see. As in, actually physically write down. Now you can actually, grab a piece of paper and write down all the terms like you're seeing here on the right. Or you can use LaTeX. LaTeX is a scripting language that allows you to, it's like programming, right? You can use some code and it will produce this nicely written, well-formatted expression. So here I took f of x given alpha or beta, these are Greek letters, and I put it here. So laser focus on every single term, right? I want to know what this is. Then I have an x. I want to know what x stands for. What does alpha stand for? What does beta stand for? What does E stand for? And what does gamma stand for? That's the capital letter gamma. So first thing you want to do is write them all down. Remember I told you earlier that you cannot keep more than 4 things simultaneously in your train of thought. There's definitely more than 4 items in here. So don't try to make sense of it just by looking at it. Actually write it down. And then once you've written it down, you want to go through the list and one by one find out what each and every single symbol stands for. What is F? What is X? What is A? What is B? What is gamma? What is alpha? What is beta? And you do not move past this expression. You do not go to the next page unless you know exactly what all of these symbols are. How do you find out what these symbols are? And I'm going to go back to why I said the text is superior to video. Here's how I go about defining, understanding how and why a mathematical expression is written certain way. What you see on the right is a screenshot of a book. And specifically, it's the index. So every textbook, and actually almost all books, textbook, non-fiction, what have you, at the end of the book, they have an index. They may have an index and an appendix, but they have an index where they list all the terms and the page in which that term is defined or referenced. So for example, here at the end of the book, under the section G, words that begin with the letter G, there was gamma distribution. So I wanted to know, what is the gamma distribution? What is it used for? What does it look like? What did the symbols mean, right? So it says if you want to see the definition of gamma distribution, go to page 231. Okay, perfect. We'll go to page 231, and this is a screenshot of that part of the page where the gamma distribution is defined. And in fact, it says here definition. Definition. A continuous random variable said to have a gamma distribution, blah, blah, blah. And then the formula is given here. Now, notice, even before I get to the mathematical expression, I'm seeing terms. Remember, at the start of the presentation, I said you will encounter two obstacles: terms, mathematical notation. So, for example, you have continuous, random variable, X, distribution, PDF. I mean, how many terms is that? 1, 2, 3, 4, 5. 5 terms before I even got to the expression. So that list I showed you earlier would actually grow. But these new 5 items will go at the bottom. So if we had this list up here, continuous, random, variable, capital X, PDF, they would go at the end of this list. Okay, write down everything. Terms and symbols. Assuming you don't know what any of these things are. So I'm going to assume that, you don't know what any of these words or symbols are. You see a mathematical expression like this. This is actually an equation because we have an equal sign. But we have expressions on the left side, expressions on the right, and expression on the right side. And this, weird-looking thing with small letters, big letters, Greek letters, English letters. What's going on in here? So when I say enumerate, I mean you want to go through all of everything from left to right, and then list them down, write them down. And then after you've listed down all these symbols, you want to go through the process of defining them. What does X mean? Why is it there? Why is gamma there? Why is beta there? And so on. And the way you would do it, ideally, assuming you have your books, let's say stack of books or PDFs or whatever you like, you would take that book. Now, this book is called Mathematical Statistics with Modern Applications. So you would go to the end of the book where it says index, and then you have all of the terms used in the book, or almost all of the terms used in the book, technical terms, sorted alphabetically. And then for this one, this is a screenshot of that page where gamma distribution is listed, right? So it says gamma distribution. If you want the definition, go to page 231. And so we flip over to page 231. And what I was saying is that before we even got to the formula for the gamma distribution, we were, presented with words like continuous, random variable, and then the letter X, which is not even here. It's not even in the equation. The word PDF, right? So if you see terms like this and you don't know what they are, go ahead and also write them down. So this list that I was talking about, continuous, random, variable, big X, these would go at the bottom of this list. So do not lose. You will not be able to keep track of everything. Do not attempt to keep things in your mind. You will not succeed. Write them down. And then once you've written them down, like a grocery list, go through each and every item. Now, perfect. It gives us a definition. So it tells us that alpha and beta are parameters. Alpha and beta are parameters, but it doesn't say anything about gamma. It's right there. And we don't know what the word's parameters are. So what do we do? All right. Let's begin with gamma, right? Let's say we know what alpha and beta are. How do we find out what gamma is? It's right there in the equation, but they're not telling us what this is about. So what we would do is we would go right back to the index. If we go right back to the index, it says gamma function. If you want to know what the gamma function is, go to page, for example, 19. Now, this is actually a screenshot from another book. In the actual book, this book with the title Mathematical Statistics, when you go to the gamma function, it just tells you the formula, but not what the symbols stand for. Because you will not pick up a book called Mathematical Statistics unless you have covered their prerequisites. If you do not know what a gamma function is, the book Mathematical Statistics is not going to cover it. So the author is going to assume you know what it is. So even if I don't have it in here, it doesn't really matter because that book did not even talk about the gamma function. It merely, like in a few words, said, by the way, this is the formula. That's it. So what do? We can't go any further and we cannot progress. Our definition is not complete unless we know exactly what gamma function is. So we pick up another book. And this book actually goes into it some more, but not entirely. So it says if you want to know what the gamma function is, the definition, go to page 19. All right, so we go to page 19 and it says gamma function. Look at this. So do you see the integration here, the integral over here? Right, that is what gamma stands for. So this one tiny Greek letter is actually equivalent to that. That is its definition. But then, all right, I mean, that just gives us more terms to write down, right? So we know what the symbols are. It tells us that it satisfies n-1 factorial. So you have this exclamation mark. There's this exclamation mark. Let's say you have not seen it before or you don't remember what it is. And it says it generalizes the factorial function. Oh, what is the factorial function? Now, it so happens this book doesn't talk about the factorial function because this book assumes you know what the factorial function is, right? The previous book had some assumptions. This book has some assumptions. Okay, so we need to know what the factorial is. So what does the gamma function do? If in order for us to know what the gamma function does, it seems that we need to know what the factorial function does. So we go to another book, a more elementary book, a more basic book. And that book says if you want to know what the factorial is, go to page 34. So again, these are three separate books, okay? Well, all right, so we flip to page 34 and it says the factorial is basically this, right? So for example, if you have n, it's a number. Pick 5. Whenever I see n, I choose number 5. If you have 5 exclamation, that means you're multiplying 5, 4, 3, 2, 1. If you had 10 factorial, if you had 10 exclamation mark, that will be 10 times 9 times 8 times 7, 8, 6, 5, all the way down to 1. That's what factorial is. Okay? Easy enough. So what does it mean to generalize? Now it says that basically what it's saying is that the gamma function does exactly what factorial does, but for complex numbers. Or let's just say real numbers. So for example, if we're talking about 5 factorial, 5 and 4 and 3, these are all whole numbers. There are no decimals involved. But what if you want to do the factorial thing, but for real numbers? Let's say you have 5.5 factorial. How do you do that? Gamma function. So the gamma function, that's what it means by it generalizes the factorial function. The factorial only works for whole numbers. The gamma function works for real numbers. So you can have fractions in there. That's what it means. So here's the recursive part, right? So we've enumerated, we've looked up the terms, and now we continue this recursively. So after we understand what factorial notation is, in actuality, right, you would spend more time. You might have to go through several books. In fact, you might even have to spend time searching for the right book. I had to actually go through several books to find the screenshots here. But keep track. That's what I'm trying to get at. Keep track of what you're doing. Don't get flustered or try to find one video that will make that will answer all of your questions. It's not gonna happen. But now that I know what the factorial notation is, I can go up here and let's say I'm satisfied. I now understand what the gamma function does. Perfect. Now that I know what the gamma function does, I will understand its role in the gamma distribution. My point is, I have gone through this, let's say I've gone down this rabbit hole, so to speak, and I've understood what this one letter does. So it's one letter, but look at all the open the new Pandora's box. So I had to go down this chain to understand what the gamma function is all about. But it doesn't change the system, right? You would keep on going through each single term. For example, here we have random variable, right? Let's say you do not know what a random variable is. Go to the index of the book. Which page is random variable defined? Page 50. Perfect. Let's go to page 50. If it gives a satisfactory answer, perfect. If not, we go to another book. Index of the book, see if we can find random variable. Did we get the definition we want? No, we'll go with another book. And you will keep on doing this until you found a satisfying definition. We do this for the gamma function, and then we do it for alpha, and then beta, and then so on, until you've understood every single symbol. So to truly understand what this one formula does, you will end up going through several books. So if you are going to study mathematics for data scientists, you need to make sure you have your resources prepared in advance. In fact, I do this all the time. I regularly visit a bookstore. Every now and then I just go there, look up the books. If I find something interesting that I might need later on, I pick it up and I buy it. There are PDFs that I purchase, university lectures. So I bookmark these ahead of time so that when time comes and I have to look up something, I have resources to look at. I'm not going to go on Wikipedia and YouTube and then watch hours of videos. I'm going to do exactly what I talked about. Now, if you're going to define, so we said we have three parts: definition, application, derivation. So the first thing we want to do is define what those symbols are. But now let's say we know what those symbols are. We know what gamma is, what factorial is. We know what alpha, beta. We know all of this stuff. Where is it used? See that if I come up here, this page doesn't talk about it. In fact, I flipped to this book. It gives very, let's say, inadequate examples of how the gamma distribution is and where it's used, right? Because again, the author assumes you have some background in statistics, right? This is more advanced. So if you want the definition, you will go to strictly mathematical books. To understand the applications of the gamma distribution or regression or neural networks or decision trees, what have you, in my opinion, the books that do a great job of explaining the applications, the use cases of these mathematical techniques are books that are not even meant for the books on that branch of mathematics. So it's not a book on probability theory. For example, I found that books on economics do a great job talking and giving examples of the use of regression, giving examples of why linear algebra would be used, right? So look for applied books. It could be physics if that interests you. Find something that interests you. It could be physics, psychology. Oh, for that matter, one of my favorite books that explains regression is actually, it has the word regression on it, but it's actually for psychology. All the examples are from psychology. And the authors of that book are psychologists. They're not mathematicians, but they do such a great job of explaining why you would use regression and how you would perform regression analysis. Why, for example, the residuals have to be normally distributed. Again, it doesn't matter if you do not know what these words are. I'm just saying that if you want to see use cases of a particular mathematical expression or formula, look outside the mathematics department. Okay, economics, by the way, is I think is interesting. Many people could be interested in how markets work, how businesses work. It could be sports, you name it. And then we have the derivation. Again, the formulas that we looked at, they're very nice, compact, sleek, right? I mean, if I go up here, if I go back to the slide again, look at it. It's actually beautiful in its own way. It's very compact. But this is not how it started off. The person who derived this did not start off this way. There was a lot of mess on the blackboard or the chalkboard, and then eventually they saw a pattern and said, hey, you know what? I can condense this into this. Like equals mc squared. So what you want to do is see how this was derived. By the way, the way I found out that this is related to the exponential and Poisson distributions was not from the book. I went through several books to find out why this thing is arranged this way. Why put B? Why put A? Why not another letter? When I looked up the derivation of it, the proof for this formula, that's where I realized, this comes from Poisson distribution. I see. And I found this true for other cases where I was trying to make sense of a formula. Now, lecture notes. For derivation, proofs of theorems are quite lengthy because a lot of explanation, a lot of words are involved. And because they are, since, for example, a book on mathematical statistics, if the author had to show a proof for every single theorem, it will be several volumes big. So practically speaking, you will not find derivations in the book. Or if you do, it will be for something that is so important, and it will be you will find only a few proofs in the book because, again, a lot of explanation will be involved. But a great resource to find derivations or proofs for theorems would be lecture notes. So you would go to Google and you would type, for example, proof of gamma distribution, and you would type the word PDF. PDF, the file format, right? Because university lecturers, professors, they write their notes and upload them on PDF files. So you can find them quickly. They're well formatted. So if you want to thoroughly appreciate, completely understand what a mathematical expression is about, you want to make sure you've done all three. You've looked up the definition. You know exactly what the symbols are. You know why they are used, why it's used, why it's relevant, actual application in the real world, and then how it was derived. This will bring you to mastery. And let me just go back up one more time. This process, enumeration, lookup, and recursion, could take several days. Because I don't know about you, but you may have adequate number of books. You may not have books at all. So it might take you a while. But be patient. But it's important that you enumerate because this way you will not lose track of what you're doing. This template, for me at least, works very well. I would actually challenge you to bring me a mathematical expression and say, Danny, tell me what this does. And I would use the system, and I could, in the span of 30 minutes or 2 hours at most, give you an explanation of the formula. Google is filled with articles, videos that are published by hobbyists. And these articles, these videos are very frequently full of mistakes. They give incorrect definitions. Now for math, it's not something trendy, or at least it's not perceived so, but in programming, right? So if you were to type, what is GPT? You'd have hundreds of people talking about ChatGPT. Almost none of them actually know how it works. They're not practitioners. And so they give their incorrect definition and they state it with confidence, right? Ironically, ChatGPT itself does that, but that's besides the point. I've seen this countless times where someone tries to explain how a machine learning model works, but they actually misunderstood how it actually works. And so you are reading this blog or article or watching this video, but you have no way of ascertaining the correctness of the claims. How do you know if this is correct or not? Well, one way to do that is to look up the author, right? If the author is an expert in the field, that's as good as you can get. Especially now, the reason I say textbooks or books in general is because they're peer-reviewed, right? You cannot a publisher will not allow you to just ship books if you have, like serious factual errors. Whereas the internet is free. Anyone can say and claim anything they want, right? Again, I'm saying this while I'm doing on a meetup. How many of you have looked me up? I could be making up everything I said could be incorrect. Hopefully, most of what I said is correct, but my point is always make sure you're getting excellent material. Unless I usually watch math videos on YouTube pretty interesting. Well, yeah, again, I'm not saying the internet is bad. I'm just saying the internet is a mixed bag. You have excellent videos, explanations from professors, like MIT has open courses, right? They're the best. I mean, you're getting it straight from the classrooms. But this stuff, this learning template wouldn't work in video, right? Because if you're watching a video, you have to like hit play, sit back, and wait for and hope for the person to actually define. But for example, let's say you were watching this in a video tutorial or a university lecture. The professor, right, could talk about the gamma distribution, but not actually tell you what the gamma function is. What are you going to do? One thing you could do is turn on the transcripts or download the transcripts and see what part of the video that word is mentioned, like closed captions, or you can download all of the subtitles. But if you download the subtitles, what are you doing? You're actually reading text. So you're back to reading text. So it's actually better to read text. Now that I've talked about the importance of books and why it's more efficient to actually learn from books, it would make sense for me to suggest some titles to help you with your learning process. Now, I did not have time to compile a comprehensive list of books, and my recommendations to you would depend on how advanced you are in mathematics and in what area your focus is in. I am compiling a list in a separate document. So if you're looking for recommended books, please have a look at the video description where you'll find the link to the recommended reading list. But that's it for today's session, everybody. I want to thank you so much for joining me today. And I look forward to seeing you in the next one. Till next time, take care and enjoy the rest of your day. Bye-bye for now.